pleasure of advising Amanda Adams and Tim Crow, and they've been working on the same bridge design project that the previous group talked about. So I'll let them talk about that now.
Thanks, Professor Hall. Like you said, I'm Amanda Adams. This is Timothy Crow. We were tasked to design the bridge crossing Flat Creek in Cannelberg, Indiana, which includes the structural analysis and the design of the reinforced concrete. As an overview of this presentation, we're going to go through the scope of the project, the loads and loading factors on the bridge, the design of the deck, beams, and piers, the design of the abutments and foundations, and the cost analysis for the project. Here is a photo of the site. You can see Flat Creek there. The location of the bridge is going to be going right by those trees in the background. And on the left of the picture, there's a copse of trees. Up that hill is where the owner's property is going to be. As you can tell, it's an agricultural use, flat field, so the floodplain for this creek is rather large. The scope of the project includes designing a private access bridge that is structurally sound, that meets American Association of State Highway and Transportation Officials, or AASHTO code, and meets American Concrete Institutions Code, that's ACI, and it also must be cost effective. From the previous group's project, Aaron and Brian came up with a design of the bridge to be 250 feet in span. It must have 3 piers at 62.5 foot spacing, and the pier height from the bottom chord of the deck to the ground is 4 feet. The loads on the bridge include dead and live loads. Dead loads consist of the concrete deck and an asphalt layer. And for our construction purposes, or our design purposes, we did not design the asphalt layer, but it's a possibility that the owner might add asphalt in the future, so we included it in our dead loads. We also included the weight of the concrete parapets or guardrails, the weight of the concrete beams, the piers, and the earth load acting on the abutments. The live load was HL93 loading, that's highway loading, 1993. 93 was the year it was added into AASHTO code. This is an image, a diagram of HL93 loading. This is the vehicle specified by the owner to be accessing the bridge. As you can see, there are 2 axles, 25,000 pounds or 25 kips per axle. Also in the live load was a braking load and the water pressure of the stream acting on the piers.
So according to AASHTO, we need to consider all these loading factors and combinations. The dead load factor was just a simple calculation, and for the live load we have a braking factor and a dynamic load factor. The dynamic load factor is for when a vehicle is driving across the bridge, but also bouncing. We consider strength state 2 and extreme event 2. Strength state 2 is a owner-defined vehicle, and extreme event 2 is the same loading combination, but a reduced live load factor and a ice factor, as well as a flood factor. Strength state 2 controlled in our case and was the basis for the design due to the reduced live load factor. So to design the structure, we had to start from the top. Starting with the deck, we had to use RISA to get the moments for our deck, and we had a distributed live load which came from the 7-inch minimum code according to AASHTO. Also, we had a moving live load that moved across the deck in 1 foot increments. You can see that the green nodes there are where the beams would be in real life. We use these factors to multiply those loading to get our largest negative moment of 19.1 kip feet and our largest positive moment of 23.6 kip feet. We had to get 2 different moments because the equivalent strip width is based on the sign of the moment. The equivalent strip width is an analysis technique that can be used to break apart the deck because it will be the same throughout the entire deck. We analyzed our deck as a doubly reinforced beam having top steel and bottom steel to meet the moment demand symmetrically. For our purposes, the compressive strength of the concrete, of all the concrete, is 4 KSI. Here's an image of our final cross section. You can tell that we stayed with the minimum 7-inch depth of the deck. but our equivalent strip width is 59 inches due to the positive moment controlling. We have number 3 reinforcing throughout the deck at roughly 6-inch spacing. The temperature and shrinkage steel runs longitudinally throughout the entire bridge, and those were also number 3s. We met the reinforcement ratio of AASHTO by having 2 layers. So to start the beam, we used RISA again to model the shear reinforcement. We got the shear amount at the beginning of the beam and at the midspan of the beam, and plotted those to get the blue line, which is the demand. To get the capacity of the shear, we had to add in the shear strength of the concrete plus the shear strength of the steel, which is the yellow line, which is called PVN. We have a step down there because we reduced the size of the steel to be more effective in our design, but the spacing stayed consistent throughout the entire beam. So our deck is to be cast monolithically with the beams, which allows the deck to act as a flange and allows it to be analyzed as a T-beam, which would be doubly reinforced considering the temperature and shrinkage steel above the beam itself. For our purposes, we had 2 cases, an inner beam and an outer beam. These 2 cases had different loadings. The inner beams having the weight of the deck, the asphalt layer, and the full HL93 at the worst case scenario of the midspan. The outer beam would only have a fraction of that HL93 plus the deck walls, which adds a significant weight to it. But the inner beams, even having a larger effective width, still controlled, and for constructability, all beams would be constructed to be that size. Here's a final cross-section of our bridge. The beams turned out to be 26 by 20 inches through an iterative process using spreadsheets. We had 12 number 10s at the bottom in 2 layers, 6 each layer. Also, we had 2 different shear reinforcing, number 5 and number 3. We had to check against deflections, but AASHTO doesn't define any deflection requirements as long as the driver feels safe while going across. But we added the ACI deflection code, which we met. The pier design was based on the hydraulic analysis for their worst case scenario of the backwater from IDNR. For them, that was a 2-foot wide square pier. So using that as our basis, we, according to ACI, had to put in 1% of the gross area in reinforcing. So that's where we got the size of our steel. And then we evenly distributed the amount of bars that we needed throughout to meet the clear cover requirement according to ACI, which was 9-inch spacing. We also had to throw in ties according to ACI, which were just the minimal number 3 ties. We then checked against the loading cases. The one on the left was the controlling state where we had the pier acting as a retaining wall, holding in the earth from the stream. We also, on that, we had the dead and live loads on top of the pier, plus the braking load acting 6 feet above the pier. The stream pressure on the right did not control because the stream didn't move fast enough to cause a big enough pressure.
For the design of the abutments and the abutment foundations, I decided to use backfill from the nearby hill. That serves 2 purposes. It smooths out the surface of the roadway as well as providing a readily accessible site or source of backfill for the material behind the abutment. So because of that, because I was choosing soil from the site, I had to find the soil properties for the soil. I did this using Indiana Geological Survey's website. They call out a description of the soil, and based on that description, I was able to determine the soil properties, such as the unit weight of the soil and the internal angle of friction. And from these properties, I was able to do some calculations under this loading scenario. This is the water and flood state under the 100-year flood, burial depth of 4 feet. And I checked against overturning, sliding, and the bearing capacity of the abutment. Bearing capacity turned out to be the determining factor there. My factor of safety ended up being a little over 3, which is the minimum requirement. And based on that scenario, my factor of safety for sliding and overturning were 100 and 500 respectively. The foundation design was similar. I used that same soil properties to determine the bearing capacity of the soil under the pier footing. I also had to include the dead and live loads on the pier. That's the dead load, the weight of the bridge and deck, and the pier itself, as well as the live load of the HL93 truck. My depth of bury here was also 4 feet. And under this scenario, I came up with a factor of safety of just over 3 as well. So then for the cost analysis, I included the earthwork, the creation of the pour forms for the concrete, and the cast in place concrete, which includes the reinforcing steel and finishing of the concrete. I did not include site preparation, which would be those stuff like creating a gravel drive for the workers or a parking lot and facilities for the workers on the job. I also did not include the review of our design by a stamped engineer. For this work, for the estimation, I consulted RS Means Guide of 2011. This is a cost of construction analysis tool. Because I used the 2011 version, though, I had to adjust for inflation over those 4 years, so I consulted the Consumer Price Index to account for that. These prices include profit and overhead as well. So here's a breakdown of our costs. Excavation and backfill have the same cubic yardage because I'm taking just what I need from the hill. The footings, piers and abutments, beams, and deck are all just the cubic yardage of the material itself for the bridge. And the riprap is an estimation we'll probably need about 5 tons to prevent scour in the stream. So our total construction cost is about $150,000. And in conclusion, we have met the scopes of requirement for this project. We designed a bridge that was structurally sound, was up to AASHTO and ACI code, and is cost effective.
We'd like to thank Dr. Kerry Hall for his guidance throughout the project, Dr. Jason Hill for providing the project to us, Brian and Aaron for doing the preliminary estimating, Professor Amy Diekman for her geotechnical help, Donna for keeping us on schedule, and all USI faculty and staff that helped us over the years. Lastly but not leastly, our friends and family who had to put up with us throughout this entire semester. Any questions?
Any questions?
Can you go back to the cost analysis slide?
This one or
So-
the previous one?
No, that one's fine. So whenever you took off like the beams and piers, when you're saying you took off the cubic yards of the actual material, like the steels for it. So in the pricing from RS Means, did that also include pricing for the equipment? And like what type of equipment to lay the beams and piers of your bridge are you using? Are you using what type of cranes?
The guide includes cost of overhead and profit for the job. So yeah, the cost of the material and construction is included in that price.
Other questions? No other questions?
Well, I'll ask them. This is probably outside of the scope of what you guys did, but, so the last group said that they tried to make a floatable structure work, because it would be less, just as you had about 151,000, just as a rough estimate, what would a floatable structure cost if they could get it to work with the backflow?
It looks like it might be about a third of the material.
It would be significantly less because they would probably use the precast, and the only price that would be there would be to get the compacted fill in and the placement of the structure itself.
So, I guess a follow-up on that, just the previous question. What's to stop a property owner from just throwing a big culvert pipe in there and some gravel on top? Are there rules or laws that govern him, prevent him from doing that?
Yeah, the rule would be the backwater requirement. That's set in place by the Indiana Department of Natural Resources. And according to Brian and Aaron's analysis, if they were to just install a floodable structure, the backwater would be too high.
They would have to rip it out. Start again.
Other questions? Did you have the opportunity to talk to the owners, the client at all?
No.
So who was your interface? Was it a company that was,
It was the same as the previous groups. It was Jarvis. He provided the preliminary report for them, and then Brian and Aaron provided what we needed for the span and the pier spans themselves.
okay, are there any plans to present this to the potential client?
I get the understanding that it would be one of three options for the client. I don't know one of the options. I know that another one was a 300-foot bridge somewhere or under that.
All right. Any other questions? Let's give them a hand.